Welcome to our first module on the introduction to linear algebra and quantum computation. Today's lecture is about tensor products and how they apply to the description of the state of a multi-qubit system. So first, what is a tensor product? Here we assume that we are given complex vector spaces V and W of finite dimension. Now, tensor products work if the linear space is not necessarily over C, but in the scope of this course, most linear spaces are going to be over the complex numbers. So the whole point of tensor product is if we can multiply vectors, and that multiplication, which we denote with this times inside of the circle, this multiplication needs to satisfy the following properties. That is distributive over the addition, and that when you have a scalar, you can move it around. So if the lambda here is a complex number, we want it to be able to move freely between one side of the product to the other, or even outside of the product. So now what we're going to do is we're going to focus on how we can construct a product that has these properties. Okay, so we will so this will involve a little bit of a theoretical constructions. Okay, so to do this, we need to describe what is called the free vector space. Okay, so this is a very sort of interesting concept where instead of being directly the Cartesian product, what we do is we take formal sums of pairs, formal sums of elements in the Cartesian product. So for example, and all the linear combinations, with complex coefficients. So what does this mean? X here is a formal sum where I denote the addition by an O plus. So when I do that, I differentiate between V1 W1 plus V2 W2 and the pair V1 plus V2 W1 plus W2. So let's write it up. What we're saying is that essentially V1 W1 formal sum with V2 W2 is not the same, is treated differently than the pair V1 plus V2 W1 plus W2, okay? These are two different elements when we consider them in the free vector space. Now, we also consider for every element, we also consider for lambda in C, we also look at the outer multiplication formally in the sense that we consider elements of the form lambda V1 W1, for example. Okay, so we look at all the linear combinations that are created by considering the sum between elements to be formal in the sense that it does not recombine by saying, oh, we'll take the sum of the first components and then the sum of the second component, okay? And now what we're going to do is, so this is a very, very large space, by the way, not just infinite, but also with infinite dimension. So we're talking about something humongous. We started off with vector spaces with finite dimension, and now we're looking at something large, very, very large. Now, we're going to use this to create the tensor product, but the tensor product in the end will also be something with finite dimension. So, what do we do to narrow it down a little bit? We define an equivalence relation, okay? So an equivalence relations between elements of the free vector space, okay? Now, we'll see in the next slide why we want an equivalence relation, but just in anticipation for that, that equivalence relation will serve us to identify elements who are equivalent to each other, okay, in the tensor product. But first, let's see how we could define an equivalence relation on the free vector space. So we need a subspace we will denote S that is made of a lot of elements in the free vector space and all the span of these elements. So everything that they span, every linear combination of elements so that will be a subvector space. And the equivalence relation is defined as follows. We say X is equivalent to Y if and only if the difference of X and Y is in this space S. Now, how is this space defined? Well, this space is defined exactly how we want it to be, so that when we consider the equivalence relations, we will have the right properties of tensor product with respect to the addition and moving along the scalars. So what it means here is we have elements that we will declare by definition that they span the subset S. They're well chosen for the right properties of the tensor product to occur. So what it means here is that we want all the elements that are defined under the point 1. So all V1, for all V1 and V2 and V and W in W, we want these elements, okay? So this thing here is a formal minus, so it's like the opposite of the formal plus, okay? And then so we want that the element of the form V1 plus V2W minus V1W minus V2W be an element in S. Likewise, we want the same thing to happen on the second coordinate. And then we also want elements of this shape, K times VW formal minus KVW, and the same on the other coordinate. Now, S is a vector space, so it does not just contain those elements, but rather all the possible sums and product with scalar and all the linear combinations of elements of this form. So we're talking about something that is a big set of linear combinations of elements of the type 1, 2, 3, and 4 that we just described. Okay? Now, let's see what's the whole point of having this. We define the tensor product as the set of equivalence classes. So we denote this bar here, that looks like a division by the equivalent symbol, is the set of equivalence classes. The space, as a matter of fact, because this can be equipped by an addition and a multiplication by complex numbers. So what does this mean? We have a map where we'll take V, we'll define, so VW bar, so this is the set of all the elements in the free vector space, such that X is equivalent to VW. And then VW bar is defined as X tensor W. Now let's show that in fact we get the kind of relationships that we wanted. Remember that S contains elements of the form V1 plus V2 W formal minus V1 W formal plus V2 W. Okay, so this is contained in S. So what does this mean? This means that we have V1 plus V2 W is in the same equivalence class, or we could say is equivalent to the elements V1W formal plus V2W. So what that means is that we have that V1 plus V2 tensor product W, which is by definition the class of V1 plus V2 W, that equals the class of V1W plus V2W, which itself is the class of VW plus the class, V1W plus the class of V2W, and this is V1 tensor W, and this is V2 tensor W. So what have we proved here? Thanks to the definition of our equivalence relation and all the elements that we ensured were going to span the space S, we have the right relationships between our equivalence classes. Okay, so what it means is the tensor product as defined here has the right properties, the ones that we want, distributivity from the left, from the right, and also we could show easily, but we're not going to do it in the interest of time, that it also holds true that you can move around those scalars just by doing the same sort of manipulation I just did to prove that first of all the properties that we wanted. So here is the thing. We also have something really important about the dimension, namely that we started off with a dimensional M vector space V and a dimensional N vector space W, and it turns out the dimension of the resulting tensor product is also finite dimensional. That is the product of all of both dimensions. Okay, so this is something that we prove in the notes of this class, but we're not going to write down the exact proof here. But quite naturally, if you have a basis of V and a basis of W, then the tensors of the elements of the basis of V and that of W form a basis of V tensor W. So here you have all the possible pairs I, for I ranging between 1 and M, and J ranging between 1 and N. Okay, and then thanks to the distributivity of the product over so addition, then what we have is we can easily write down, if you write down an element of V according to its basis and an element W according to the basis of W, then you have this straightforward formula to give you the element with respect to the basis V tensor W. Now, there's a really important point here that needs to be made before we move further. What I'm describing here is what is called a pure tensor, so an element of the form V tensor W, where V is in V and W is in W, and I expanded it with respect to the basis. Now, you have to, so the proof is a little more involved than that, because we need to consider that not every element of V tensor W is of the form small v tensor W, okay? So this is something that needs to be really well understood, that it's not, these are pure tensor and these are a special case, okay? Now, even though these are a special case, every element in V tensor W can be expressed as a linear combination of these elements. Okay, so despite the fact that they're not of this, all of this form, they still will be in the span. Every element of V tensor W still will be in the span of the basis xi tensor yj for I and j, ranging between 1 and m respectively, 1 and n. Okay, so this is something that needs to be, and we'll come back to it when we talk about entangled states a little bit down the road during this lecture. So, for example, so here we're looking at V and W. So this is a very simple example. They're both C2s. And what is the basis? Well, we'll have that 0 tensor 0, then 0 tensor 1, then 1 tensor 0. So I'm just trying every possibility here. Okay. A notation just that we might use in the future, we also sometimes use this, okay? Now, what does this mean? You have expansion you can expand those kinds of products of sums in this way. For example, you have 0 tensor 0 plus 0 tensor 1 plus 1 tensor 0 plus 1 tensor 1. And in general, if you have A, B, C, and D complex numbers, you'll have, of course, and that's exactly what gives you the formula, the big formula that we had in the previous slide, that AC, this is AC 0, 0 plus AD 0, 1 plus BC 1, 0 plus BD 1, 1. Now, we also will need to extend the inner product. We had inner product in V, we have inner product in W, now we want inner product in V tensor W. Okay, so how are we going to do this? Well, we'll extend in a very natural way. The way every linear or multilinear map is defined on tensor products is usually by first defining it on the pure tensors, which, remember, is not the whole set, not the whole space V tensor W. However, it's usually enough to say once it's defined on pure tensors, so tensors of the form V tensor W for V and W, then it can be easily extended by linearity over all tensors in V tensor W. So how do we define our inner product is by saying that on our pure tensors we've got that V tensor W, and I'm looking at Ketz here, tensor, let's say W prime V prime is going to be, by definition, V inner product with V prime times, that's just the regular multiplication, V W, W inner product with W prime, okay? Now, once we know that, by multilinearity, so just by replacing V and V prime, what do we get? We get a straight formula, and then we can of course extend this to by bilinearity of the inner product. You can extend this formula to any tensor. This is again an inner product between two pure tensors. Okay, but you can have the same. You can extend this by saying, well, I take a linear combination of elements of this form, and I proceed by multilinearity. Now you notice here that in the most general case, we're looking at something very ugly. Okay, this is actually a quadruple sum because we sum over I, K, J, and L. And we basically need all the terms here. So all the all the inner products of xi by xk's and all the inner product of yj by yl. So we have actually 4 indices in our sum. So it's a pretty big mess. So let's just work it out on an example. Here, what we're asking is for the inner product between this part here and this part here. And like I said before, so these are pure tensors. So what we know, we've defined our inner product on pure tensors by saying, well, this is going to be the inner product between the elements that are here and the elements that are here. Okay, so what we're going to do is to say, okay, this is going to be 0, 0, tensor 0 minus 1 times 0 plus 1, 0 plus 1 tensored with 0 plus 1. okay? So this thing is simply 1 plus 1, and this thing is just 1 minus 0, because 0 and 1 is a tensor 0. So what we get here is 2, okay? Now, let's get to an important thing here, is that we usually manipulate orthonormal basis when we do quantum computing, okay? So everything is about decomposing vectors on orthonormal bases, and like remember from the qubit chapter, and this is going to be confirmed here, that everything we do when we look at states is always by looking at orthonormal basis. So the question is, what happens when we take the tensor product of elements in orthonormal basis of V and W? Well, it turns out we'll produce an orthonormal basis because of the inner product we just defined. We'll turn it into an orthonormal basis of V tensor W. So here you see that you have a drastic simplification. I mean, you can think, well, it still looks bad, but now we're looking at a sum over only 2 indices. Okay, so what survived from the previous expression is only the terms vi, v prime I, wi, w prime, wj, w prime j. So what it means is we map. So we have this I tensor j. These guys are an orthonormal basis for the inner product that we defined from, rising from inner products on V and W. And so what we can do is, so at this point, there's no real reason for mapping them to any particular orthonormal basis of C to the product NM, all right? But up to a change of orthonormal basis, we can very much say we'll map the tensor I and J to the ijth element of the canonical basis C to the Mn, where ij is understood in the lexicographic order. So what does this mean? This means that we ordered them that way: 0, 0, then 0, 1, then dot 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 until 0 n minus 1, and then we move on to 1, 0, then 1, 1, and dot dot dot. So we continue that way, okay? And now with these kind of formulae, with this kind of ordering and the multilinearity, then we'll be able to derive straight up formulae. But of course, every formula that we will derive starting now will derive from this particular choice of ordering the elements in that order, okay? So we need to keep in mind that because there is this isomorphism here, we could have said, well, let's just look at it up to a change of basis. But now we want to fix this choice of a basis because we want to manipulate those tensors as elements of C to the Mn. So we have to sort of agree how they were mapped to specific vectors in C to the Mn. So now that we have that, we'll be able to derive precise formulae that we can use to compute on C to the Mn exactly, and not just abstractly. So, for example, if I say, oh, I want the vector 0, 1, 0 tensor 1, then what I get is the 0, 1th vector of the canonical basis of C4, and here that is just the second one, okay? So this is in fact the second vector of C4. So that gives me an actual vector in C4 I can manipulate, I can see, and I will be able to perform all the necessary operations for quantum computing. So likewise, so first off, that direct consequence of that is that once you generalize it to the case of dimension m and n respectively vector spaces, then if I give you those two vectors defined on the canonical basis, so this of course when you write down as a column vector where you're essentially doing is you're defining your vector on the canonical basis, then that gives you a straight up formula to express V tensor W on the canonical basis of C to the Mn. And so you just start V1 W1 and then V1 W2 and then on so on and so forth until you have V1 Wn, and then you move on to V2 W1 and so on and so forth until the last coefficient. And then while we're at it, we can define a tensor product of linear algebra operators. Now, let's just take a step back before defining those formulae. Let's take a step back and figure out what that is. Well, you assume you have linear maps, a linear map on V and a linear map on W. And now what you want is to see if there is any meaningful way you would derive from that a linear map from V tensor W. And the way to do it is to say, again, let's see if there is a natural way to define such a linear map on the pure tensors, which are known, they're not all the tensor product, but they're known to span the tensor product. And once you define this in this natural way, then you can say, I have in fact defined a linear map on all of V tensor W because I say by linearity, I extend this map to all linear combinations of the pure tensors. So now the question is, suppose I have a linear map defined by a matrix A and a linear map defined by a matrix B, how could I define a map on the pure tensors? Well, I could do it in a very natural way. Assume I take this pure tensor in, well, I spit out this pure tensor where I apply A to V and B to W. And if I choose to do that, all right, and I use the previous formulae, then the matrix that will give the action of that linear map on the canonical basis of the tensor product, so of C to the Mn, is going to be given by, so this is how we denote it. So these are, this is what represents the resulting matrix, okay? And this is the block matrix that will define the action of this linear map on the canonical basis of C to the Mn. So here you have coefficients of A, and each coefficient of A gets multiplied by a block of B. Okay, so this is a block of B. So this is a block matrix. And in particular, it's an n by, so n times m by n times m matrix. Okay, it's made from an n by m, and so here in the most general case, you assume that your spaces are, of course, not all same dimension. So here we have the size is n by q and p by n. Okay, in the case that you're not considering square matrices. So let's work it out on an example. So here, of course, in most of the cases, in fact, when it comes to quantum computing, we'll always most of the time, we'll be looking at square matrices. Okay, so the previous formula simplifies a little bit. And so what's going to happen here, for example, in the most simple case, let's look at 2 by 2 matrices. So we have the identity here, and we have the Hadamard matrix here. What would be, according to this formula, I tensor H? So you have blocks of H. So I can get my 1 over square root 2 out of it, because it will simplify the writing. And then I have one block of H multiplied by square root 2. And then my blocks of zeros, and another block of H, okay? So this is the sort of the way to spell out what the linear operator is. Bear in mind, though, when solving exercises, that a lot of the times I'll be asking for the action of a particular tensor product of operators on another, on the pure tensor. And if you're looking at the action on the pure tensor, it's usually easier to look at the formula, A tensor B acting on V tensor W is really AV tensor BW. Okay, so you don't always have to write down the matrix, especially because as N and M grow, the dimensions of A and B, as they grow, the dimension of this tensor product of operators, the matrix that represents it, is going to grow accordingly. So it becomes quickly very annoying to have to do that, while there is actually a very easy way to derive the action on pure tensors. So now what happens when we try to apply this to multi-qubit systems? So it turns out we postulate that when you have two qubits, so you have a 2-qubit system where qubits don't interact, the right way to describe their state is by looking at the pure tensor of their state. We call that a product state. Okay, and this is because so this is describing the system that is made of two particles that are not interacting with each other. Okay, so this is sort of the simplest kind of systems that we're going to be dealing with. But of course, much like the fact that tensor products are not, elements of the tensor products are not all pure tensors, not every state is going to be a product state. Okay, so we're going to see in a minute what it means to not be a product state. But really here, the big takeaway is that those tensor products are going to be the mathematical foundation to the description of multi-qubit states. And of course, once you've tensored C2 by C2, you can tensor another C2 and another C2. So you can describe the state of a system with arbitrarily many qubits. Okay, not just two, but it's just by iteration. Okay, so entangled states are the ones where the state of are the systems where the state is not a product state. So if you're not a product state, it means that the state that the vector that represents your state is not a pure tensor. And we've seen before, there should be a lot of them. So let's look at, for example, a prototypical one. This example is giving you the product state. It's giving you a linear combination of two product states. Now, is this a product state or an entangled state? Well, we were going to prove it has to be entangled. So let's do it. Suppose, so is this true that this is entangled? Well, suppose that psi is in fact a state of the form A0 plus B1 tensored by C0 plus D1, okay? So here what I'm doing is I'm supposing this is the case, and I'm going to see what kind of constraints do I have on the complex numbers A, B, C, and D that make this thing impossible, okay? Because this thing needs to be equal to this. So I'm gonna expand this product, and I'm gonna then identify each coefficient. So let's expand the product first. So what we have is AC 0 tensor 0 plus BD 1 tensor 1 plus AD 0 tensor 1 plus BC 1 tensor 0. Now I'm identifying with the coefficients here, okay? So what I have is this should be 1 over square root 2. This should be 1 over square root 2. This should be 0. And this should be 0. Now, I'm seeing incompatible constraints here because the fact that AC is a non-zero element means that neither A nor C can be zero. The fact that BD is a non-zero element means that neither B nor D can be zero. However, I also know that A times D, so none of A, B, C, and D can be zero according to the first two constraints. However, here I learned that either A or D should be zero, and then either B or C should be zero. Okay, so I have half my coefficients are telling me that none of the coefficients should be zero, and then the other one tells me half of my coefficients should be zero. So we have here ourselves an impossible constraint to satisfy, which means that this state cannot be a product state. And by definition, it is entangled. So now we'll see what is the consequence of being entangled, okay? But first, we need to talk about measurements. So, we've seen what it means to measure in the canonical basis or in the standard basis for one qubit state. Now, assume that you have two things you want to do. First of all, you have a multi-qubit system, okay? And assume that you want to measure it so you want to measure the first n qubits in a particular basis. So there are two different pieces of information here. First of all, I choose a basis where to measure my first n qubits. Okay, so the simplest case, of course, is when n equals 1. So I have a 2-qubit system like previously, and we're going to deal with it in the next slide. It means that I have my 1-qubit system, and I decide, oh, what kind of basis do I want to do the measurement in? Now, what does this mean? Well, it means that for all the orthonormal bases, I can say I want to measure in this basis, and I will learn one of two possibilities of my measurement. So one way to think about it is rewinding to the beam splitter experiment. When we were measuring the polarization state of a photon, every measurement apparatus was parametrized by a choice of an angle alpha with the direction according to which we were measuring. Well, that choice is precisely the choice of an orthonormal basis. Okay, so you perform a rotation from the standard basis, and this will be the choice of our orthonormal basis in which we perform the measurement. And in general, for example, if I have the plus and minus state, 1 over square root 2, 1 plus 0, and 1 over square root 2, 0 minus 1. So these plus minus states also define an orthonormal basis, and I can perform a measurement in there, okay? And the outcome will be plus or minus, and then it will collapse the state in this particular configuration. If I get plus, I get my state gets collapsed in plus. If I get minus, my state gets collapsed in minus. So here, the second component that we need to, the second thing we need to do is we need to rewrite our state according to the basis in which we're trying to measure. So what it means is we need to find that linear combination where all the gamma i's, they're not necessarily orthogonal to each other, they just have to have norm 1. Okay, so we need to massage the state so that it has this shape, and when it does, then the measurement of the first n qubits yields the answer I with probability square the norm of alpha I here, and it collapses the state to this, okay, which obviously has norm 1, and that's it. So that's sort of a generalization in two ways of the concept of measurement that we saw previously on 1-qubit systems. First of all, here we introduced the fact that we can choose the basis in which we measure, and second, we also introduced the fact that we can measure only a sort of, when we have multiple qubits, we can choose to measure only a subset of the qubits, so the system that is made out of a subset of the qubits. So that's also very important. Now let's see how it happens when our state is entangled. So that's sort of a very important case. In fact, also very interesting from a computational standpoint, because you can imagine that the kind of information you get by only looking at systems of qubit that don't interact with each other is never going to give you very interesting answers for computational problems. So the really interesting answers will come out of systems that have some degree of entanglement. So let's see what happens if I measure the qubit. So first qubit, let's say in the basis, so to simplify, in the basis 0, 1, so it's what people call sometimes the standard basis or the computational basis. This is also the canonical basis of C2. So in this basis, we're going to measure the first qubit of psi. So what do we get? Well, we will get, with probability 1/2, we get 0, and we collapse our state to the state 0, 0. And with probability 1/2, we get a 1, and we collapse our state. So our state is mapped, then it becomes 1, 1. Now, what is so interesting about this entanglement? Well, you can now choose to measure the second qubit, okay? I can say, hey, I've measured the first qubit, I've obtained a 0. Now my state has collapsed to 0, 0. Question, what is the outcome of a partial measurement on the second qubit? Well, if you reapply this recipe, you'll see that you have a 100% chance of measuring a 0 if you collapse your state in the state 0, 0. Well, you'll have a 100% chance of measuring a 1 if you had collapsed your state, if you had previously measured a 1 for the first qubit and thus collapsed the state into 1, 1. But then, what if you had measured the second qubit first? What would have been your chances of obtaining a 1 or a 0? Well, again, applying the same recipe, if you measure the second qubit first, you have only a 50-50 chance of obtaining a 0 or a 1 for the same reason your first qubit had 50-50. What it means then is that the measurement of the first qubit has modified the odds of measuring the second qubit. If we had not measured it, it would have been 50-50. But once we've measured the first qubit, then we have a 100% chance of getting 0 or the 100% chance of getting 1. So what it means is those two qubits are not independent. The measurement of 1 fixes the possible value of the second one through a second measurement afterwards. Okay, so these are not 2 degrees of freedom. They're actually what we call entangled. The way to think about it from the physical example we gave was the beam splitter, the birefringent material that was taking any state that has polarization up-down would go into one direction, let's say the vertical one, and any state of polarization left-right would go straight through the beam splitter on a horizontal path. What it creates is in the form of entanglement, where the degree of freedom polarization and the degree of freedom momentum get entangled, meaning on one path you can only find a photon that has a up-down polarization, while the polarization on the other path is directly connected to the degree of freedom momentum. Okay, here it is an abstracted version of this, where the degree of freedom where there is no longer freedom to evolve between those 2 qubits. Okay, those 2 qubits are sort of their states are intrinsically tied here. Okay, so that is a very important notion that we'll be using throughout the course. And like I said, if there is really one takeaway, is that entanglement is what makes quantum computation useful. Otherwise, what we'd be doing is simply just manipulations on independent qubits, which would never lead to interesting solutions to interesting problems. Thank you for your attention.